Right, okay, so let's have a look at question 4 now. So this looks like a number theory topic, so let's have a go. So, first question, use Fermat's little theorem to find the least positive residue of 6 to the power 542 modulo 13. So, let's first of all, we need to think about what Fermat's little theorem tells us. Now, the way that I remember it is, I think it's in the textbook as well, is that if we've got a to the p minus 1, p is a prime number, and we're taking that mod p, then this is equal to 1 mod p. So, no, I was just getting congruent to. So in this case, we're looking at modulo 13, so let's see if we can write 542 as a product. So, let's see what I can do. So I want to write it ideally as 12 times something, so that's p minus 1. So that's going to be 12 times, after the calculation rate, you can do the Euclidean algorithm if you need to, 45 plus 2. Okay, so how does that help us? Because we've now got 6 to the power 542 mod 13. And I'm now going to write that as 6 to the power of 12 to the power of 45 times 6 squared. And we're still thinking mod 13. So I can now apply Fermat's, so I should probably write it as 45 to the power 12 to make it more explicit if I wanted to. So 45 to the power 12. So applying Fermat's little theorem, this is p minus 1, this is some a, so that's going to be mod, 1 mod 13. So this is going to be 6 squared mod 13. 6 squared, of course, is 36. So we've got 36 mod 13. So then 26, if we times 13 by 2, so that means we're 10 off. So that means we're going to get 10 mod 13. So that's it. Okay, we now got possibly an unrelated question. 7 students, conveniently named A, B, C, D, E, F, G, are attended a concert and will sit in a particular row of 7 seats. We've got 7 students and 7 seats. No restrictions on where they can sit. Well, let's try and picture the situation a little bit. So you can remember all the formulas, the different combinations, but I don't think that's too helpful. So 1, 2, 3, 4, 5, 6. I've gone way too long on that. Okay, so we've got 7 seats there. So for that first option, I could have all 7 people. And for the next one, I can only have 6 people because I already picked the first one. And it'd be 5 people and so on. So this is just simply going to be 7 factorial. Now we got these 4 people sit together. Now it's going to require a bit more thinking. So 1, 2, 3, 4, 5, 6. Okay. So we could have A, E, F, G like that. And then we could have any combination, any rearrangement of that. We could have 4 people sat in these positions, 2, 3, 4, 5, in these positions, or in these positions, so thinking directly below each one. There we go, jumped the gun there, haven't I? F, G, A, F, G, and that's it, isn't it? So, we've got these, 1, 2, 3, that's because I've got 6 seats like an empty. So I could also have like that. So we've got 4 different positions where we can sit the 4 people together. So that means we're going to times something by 4. Now we need to think about the number of permutations for each particular position. So if I was looking at this one here, this row, I would have 4 factorial, coming from the fact I could have either A, E, F, G or there, but then I could only have 3 of them there, 2 of them there, and 1 of them there. And then, well, I've got 3 people left over, and they could be rearranged in 3 factorial different ways. And then I've got this happening 4 times, so it's 4 times 4 factorial times 3 factorial, which I could write as 4 factorial squared, so it's 4 factorial times 4 factorial. Both would be correct. Brenda sits at one end of the row and Graham sits at the other end. So I'm going to ignore, well, all the different seats here. But I could either have Brenda here, Graham there, Graham there, Brendan there. So that's 2 possible positions, and then we've still got 5 more people in between, so they could be rearranged in 5 factorial different ways. Okay, we've got Charles and Devrinda do not sit next to each other. So, a bit like when we talk about probability, if we're thinking about not, it's often the inverse of it being the actual case. So, let's consider all the possibilities where Charles and Devrinda do sit together, and we could subtract that from the unrestricted case that we have at the top. So, I'm going to do a little bit down here. So we could have alright, number 3, 4, 5, 6. Okay, it's not doing. I'm going to rub this bit out. Oh dear. So I could have C and D here, 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 C and D here. What have we got there? We've got 6 different positions. Okay, so that means we've got 6 different positions. And in terms of the number of rearrangements, well, there's 2 factorial ways of rearranging C and D, but there's also 5 factorial for the remaining people. So that would be our calculation for the number of ways in total. That's just going to be 6 factorial times 2 factorial, isn't it? So we want do not sit together though. So that's going to be our total number of cases, 7 factorial, subtract 6 factorial times 2 factorial. Okay, well then you should obviously get the actual values, what they are. So 7 factorial is the same as 5040. Okay, we then need to get 4 factorial squared, which is the same as 576. And then we've got 2 times 5 factorial. Just making sure I put the factorial in brackets here on the calculator just to make sure that you definitely only times in. So let's make sure it actually does that bit. So we've got 240 for that case. And then we've got 7 factorial. Take away 6 factorial times 2 factorial, which gives us 3,600. So a lot of different seating plans that could be arranged.